Hello and welcome to the AAA Prosthetics Enterprise Team. We are part of the Consumer Products Manufacturing Enterprise Group, and my name is Kiernan Dunn. Our other team members are John Stengel, Ethan Sabotta, Emily Breetine, Paige Elliott, Anna Turner, Nathan Bruckman, Jaden Foos, Charlie Lincolnhall, and Rafi Slager. We have five mechanical engineers, 4 biomedical engineers, and 1 human factors major on our team, so we're very diverse. Our advisor is John Herlevich, who is part of the chemical engineering department, and we will discuss the product description as well as different prosthetics that we've created throughout the years, testing that we've done, as well as the next steps and going forward.
Is developing a below-the-knee foot ankle prosthesis for use in developing countries. Amputees in these countries are often unable to afford prostheses currently on the market, as well as the associated medical care with those prostheses. Our design must support 300 pounds, be self-serviceable with simple tools and easy to operate, be usable in rough terrain such as sand, dirt, and gravel, have multiple degrees of freedom including inversion and eversion, it's inward and outward movement of the ankle, and cost less than $200.
Over the past 8 years, we've had 6 different designs for our foot. We started out with the original design, which is our lightest design, but we didn't really like how flexible the material was, so we moved on to the blade design, which was really light and it's small. However, we wanted to increase the load limit.
Our next 2 designs were quite the jump from the first 2 designs. We decided to include a rocking design for a better rollover effect. These 2 designs performed a lot better compared to the first 2 designs. At the same time as the Rocker 2, we created the can design. However, due to its size and shape, we quickly decided that we should move onto a different design called the arch design.
The arch design is our latest design, weighing in at a whopping 3.2 pounds. It's very large and bulky.
Looking at what is currently available on the market, our designs have been weighing heavier and larger. However, they have been able to withstand a substantially larger amount of load, and based on these data markers, our next design is going to be slimmer and incorporate a lighter weight material.
Okay, after completing 3D modeling, finite element analysis, or FEA, is completed. Here's what a typical FEA looks like for our foot designs. On the left, you can see that the constraints are applied at the bottom of the foot where that arch would meet a flat surface. And then a required force of 300 pounds is applied vertically, directly onto that ankle piece as well. And then the simulation is completed, and here's what a final simulation looks like for our arched foot design. You can see these darker spots where there's red, yellow, and green. That is where the most stress is applied to the foot. After completing the analysis, we can determine if our design passes or fails our constraints. And based on this design, all of our constraints pass.
All right, so for the gait testing portion of our project, it's one of the most important factors used in the analysis of our design. We use a goniometer to collect the data, and we attach it to the hip to measure the hip angle rotation while walking. And we designed a stilt that also connects our design to a stilt that we can perform testing on instead of using an actual amputee. We compared our designs to the natural gait, which is just a non-amputee walking and measuring the hip angle. Our Rocker 2 design had data very much comparable to the natural gait data, and then our arch design data did not perform as well compared to the natural gait data.
Ready. So for static testing of our feet, we would use a 15 and 20 degree block of wood as an ankle block, and we put the foot in a forefoot or a heel loading position. This is our forefoot loading as the toe is on the higher end of the block here. And then we would apply a force. The maximum force reached was 3,000 newtons for both heel, foot, and the rocker design, as well as this arch design. We applied it at a steady rate downward on the ankle, and we measured the deformation that happened. So this is what this looks like.
All set? Yep.
see much yet, but since it's a constant force, it's going kind of slowly, but it is applying, and you'll see towards the end, you'll see a little bit of deformation happening here. You'll see the foot conforming to the force. And then there, we can show another one. This is the rocker design. Same thing, applying the same force downward. And you can see the deformation of the foot happening slowly, but it's not too much, so it went really well. So all tests went really well, and the ultimate static force, so the ultimate 3,000 newtons was reached for each of the tests, and neither of the feet broke.
So with completing tests on the designs, we have created a design matrix. For the matrix, we gave each category a weighting for most important or least important. And as seen in the matrix, gait testing is weighted the most at 25, followed by stability and static test load. With the ratings, we also graded each category, and we gave them a rating between 1 and 5, with 5 being the best. So when we looked at all of our designs, Rocker 2 became out as above average and was the best one overall. Along with that, we also did most of the testing on the arch design, which has the best stability, but overall it came at the cost of rollover gait testing and had a lot of weight added to it.
The team had recently traveled to a conference held by the American Academy of Orthopedics and Prosthetics. Here we received a lot of valuable feedback, which is leading into the next steps that we are taking as a team. So we are looking into redesigning the prosthetic foot. We are hoping to incorporate a two-toe design, which will help with inversion and eversion, as well as increasing the range of motion. We are also going to be looking into researching different types of materials to make the prosthetic out of. This is going to help increase the flexibility of the foot, as well as making it a more lightweight model.
So considering the new materials and design, we're looking into alternative manufacturing methods to test the prosthetic with. We're looking into finding a new location to test the prosthetic in. Once we do that, we'll test the prosthetic and then finalize the design.